propose their talks, and then we arrange the event for them. Okay, so everything we do is possible thanks to our sponsors. I would say let's start with the host of tonight, Mikamai. So we already got an introduction of Mikamai, but let's thank Mikamai for hosting us tonight, please. And then this is our premium sponsor, is Oliver James. How many of you already know Oliver James? There you go. Mar is over there. So Mar is our contact person for everything related to recruiting and job openings, career coach. It's the official career coach of the community. At the moment, we have those 4 major openings that are managed by Oliver James. One is a data scientist and machine learning opening based in Florence for a technology service leader company. Another one is a senior level data scientist for a telco here in Milan. Then there is a data scientist opening for insurance company. Another one is a senior level data scientist for a telco here in Milan. Insurance. So if you want to know more, please speak with Mara. Just have a chat. Our second sponsor is GitHub. GitHub, I guess everybody knows what GitHub is. And they're investing a lot on bringing all the platform that was originally designed for developers. They extending the platform to provide more features for data scientists, not just for developers. They have a massive investment in that area, especially now that it's been acquired by Microsoft. So check it out. Then the wallboard. This is the official wallboard. Everybody, if you have any message you'd like to communicate, and we're gonna publish it on the wallboard of the community. Let's start with the Deloitte Garage Challenge. It's an online challenge. It's already started, but it's still in time if you want to participate. It's in the energy and mobility industry. It's like a hackathon. Lasts almost a couple of months, more than 2 months, but you still have time if you want to join. There are prizes, so you can go on the website and check it out. Another member of the community has recently started this new initiative, which is binarysurf.org. It's about machine learning classes in particular locations where you're gonna have both surfing school as well as coding and machine learning classes. There's another friend of the communities now, and they build the intelligent customer relationship management system based using AI and machine learning. So they're also looking for data scientists, data analysts. They have different openings. So if you're interested to know more, go on the website. Then there's Helixa. So this time, like you used to see this slide before with the name of QView, which is the company where I work for. We've been recently acquired by Helixa. So this is a very big plan now for growth, and there are a lot of openings, both senior and junior levels for data scientists and machine learning engineers. And what we do, we work in what is called the artificial social intelligence, which means building algorithms able to model the human behaviors. If you want to know more, speak with me, or there are a couple of colleagues over there. And that's it. So again, if you want to send us your messages, we're gonna be very happy to publish it. Now let's move to the real content of the evening, which is the TED Talk. We're gonna start soon, and then I guess it's gonna last maybe 1 hour, maybe 50 minutes, no more. And then there's no aperitivo tonight. But if you guys wanna stay, wanna gather together and go having dinner together. I'm not sure if I'm gonna stay later, but I'm really, welcome you to do that and spend some time together. That's it. We really need your help to spread the word. We need your help to engage other people also in the online community. So please share contents, take pictures, tweet, tag us on Twitter. We have a Facebook page. We're live on YouTube right now. as well as we have our dedicated LinkedIn group. You're gonna find us everywhere. That's it, and enjoy.
Okay?
Yeah, it's from here, just.
All right. Hi, everyone. Thank you very much for being here today. And thank you to the organizer of the Science Milan community for inviting me today, and to the hosts of this great night. So my name is Vincenzo Lomonaco. I'm a PhD student at the University of Bologna, and today I'm going to talk about continual learning with deep architectures, which is also the title of my dissertation, which is going to be out, I guess, in a few months now, and it's, of course, under the supervision of Professor Davide Maltoni at the University of Bologna. So before starting, let me say a few more words about myself. So other than a PhD student, I've been a visiting scholar at the Institut Paris in Paris, working at the intersection, I would say, between continual learning and robotics, under the supervision of Professor David Filiat. And then I've been also a visiting scholar at Purdue University for 6 months in Indiana, United States, where I worked at the intersection of continual learning and reinforcement learning. And now I'm also the PhD student's representative of the Department of Computer Science and Engineering, also in Bologna, and the Department of Computer Science, yeah. And I'm also involved in some teaching activities at the University of Bologna for the machine learning and computer architectures courses, both at the bachelor and master level. So then if you're interested in deep learning, especially within the context of the R language, there's an online course you can follow that is called Deep Learning with R, and then the book on the same topic that I've been reviewed that is called R Deep Learning Essentials. But last but not least, I'm also the founder of Continual AI, which is an open community of researchers and enthusiasts who share this interest in continual learning, especially in the context of deep learning. And the idea here was to connect people, essentially, because it's a pretty new topic. It's within the deep learning community. And so the idea was to connect people, researchers, enthusiasts, developers, data scientists, and try to do more in this topic that we think is fundamental for the future of AI in general. So I invite you to visit the website of the organization, which is going to be an official non-profit research organization in the few next weeks. And it's continualai.org, or you can join directly the Slack channel, which is our preferred channel to speak about continual learning and exchange material and so on and so forth. So let's now speak about the actual workshop of today. So this is the outline, but I don't know if we are going to cover all this material in just 1 hour, but I think that the organizers are going to let these slides to be published online, and I see there's all the streaming services that you can use to recover the material. And well, yeah, so we're going to start with an introduction to continual learning, what is continual learning, why it is useful, and why it's important. And then we will move to the core part of this workshop, which is the hands-on session of around 40 minutes, depending on your level. So if you have a laptop, you can join me and work on it using Google Collaboratory, that I think some of you may know already. And then we will move to a description of more recent stuff, especially in the research area of this topic. So a new benchmarks for 50, a new strategy R1, and then a few ideas of how to mold together continual learning with other paradigms like unsupervised reinforcement learning, and then in the end, how can all this stuff be applied to real world problems, today? So let's dive right in. So as you may know, deep learning holds state-of-the-art performances in many tasks. Vision, language, natural language processing, speech recognition, and so on and so forth. But much of this success is due to supervised training from huge and fixed data sets which are representative enough of the problem we would like to tackle, right? However, no matter how big your training data is, your data set is, as we grow in terms of data dimensionality and we would like to solve more and more complex problems, not toy problems, it becomes exponentially more difficult to cover the entire space of possibilities with a representative data set collected a priori, right? In our life, it's really impossible to cover all the space of possibility before starting our life. So we have to explore it and we have to adapt to it. And as you can see here on the bottom left, these 4 images are 4 images that maximize the output probability for the Barber class of a trained network on a very big data set that is ImageNet of more than 1 billion images inside. So it's a very big data set. Nevertheless, the network has a very biased understanding about the Barber class, which, as you can see, includes also people arms. So the network has this understanding of the class barbell and is a biased understanding, even though it has been trained on millions of images. So we cannot pretend a network is going to be able to learn perfectly every possible concept because the space is just too big to cover with a representative data set. And the same happens in many contexts, and you can find thousands of different errors a prediction model can do because it has essentially a biased understanding of the external world. So in this case, a very uncommon picture of flooding is described by a captioning neural network as a group of people standing on top of a beach. Because it's very difficult that you'll find a very good representative data set for flooding pictures, and so on and so forth. So you'll find thousands of these examples, but the truth is it's very difficult to cover the narrow subspaces of this entire volume of possibilities. And so how can we still improve AI scalability and adaptability? That is how we can scale in terms of intelligence while being sustainable in terms of computational and memory resources, and how we can adapt to new circumstances we have never seen before. And the answer to us is to never stop learning, so like our brain does. And essentially, explore this huge volume of possibility just locally and as we need it, breaking this very rigid paradigm of training offline and then deploying a prediction model and moving towards a more smooth, let's say, natural way of learning where we constantly adapt our prediction model to fit our new needs. And practically speaking, this translates in this. So as we learn mapping function f of theta, our neural network, from the x1 distribution to the y1 distribution, then what we would like to do as we encounter a new pair of input and output distributions, what we would like to do is to update our prediction model so that it can handle both mappings, but without any more accessing to the previous input and output distributions. And so that we have a single model, always updating and generalizing over time. So continual learning is the only paradigm that can deal with a higher and more realistic time scale where data and possibly tasks become available only during time. We have no access to previously encountered data, so when it passes, it's gone. And this allows us to be constant in terms of computational and memory resources that we deploy for our AI system. And hence incrementally developing more complex knowledge and skills. So why continual learning is a fun, challenging problem then? It turns out that like many connectionist models out there, gradient-based end-to-end gradient-based architectures such as neural networks, they suffer from a problem known in literature as catastrophic forgetting. That means that once you train a network on a piece of data, then you expose these data to a new data distribution, new examples, without having access to the previous ones, then all the past knowledge is completely erased, it's overwritten, if the parameters of the network are overwritten to suit just a new data distribution. And in this animated GIF, you can see an instance of this problem for a simple, let's say, standard object recognition task. So in which we encounter a number of training batches over time, in this case 9, in which that contains essentially different objects we have never seen before. So, and as we move on and we learn about a new bunch of objects, we completely erase our knowledge to distinguish the previous ones. As you can also tell from the confusion matrix on the right, where these vertical bands essentially are saying that the network at every step are just guessing among the newest objects it is facing. So in the last decade, I would say we have seen a number of strategies, approaches to tame essentially forgetting, which is the #1 problem in continual learning. And we can conveniently frame them in 3 big groups. So the architectural approach, the regularization approach, and the rehearsal approach. The first one is based on the idea of changing the architecture of the network to preserve all the information and to make space maybe for new information to be stored inside the network. And so it's based on freezing some weights of the network or adding a few layers or whatever regarding the architectural composition of your model. And while the regularization approach is more based on the idea of regularizing learning when approaching a new data distribution and trying to somehow change as little as possible the weights, the parameters that are important for the previous distributions. Then the third group, the third approach, is based on the idea of having a fixed external memory size that we can use to store old patterns that are maybe very representative of the previous distributions we have encountered, so that we can rehearse from them while we learn about new data distributions from new examples that we encounter. So in the next hands-on session, we're gonna try to implement 2 at least of these continual learning strategies. The pure rehearsal one, in which we just store all the previous patterns, previous examples we have seen in the previous tasks, for example. And we use this example shuffle within the new data that are coming, or the new task, and then we essentially update our model with all these new data. And of course, this strategy is pretty non-efficient, and it will be our let's say upper bound, because of course it has the best accuracy. But then we are gonna see the next strategy, which is a regularization one, AWC, from Elastic Way Consolidation, that was proposed in 2016 by DeepMind, and it's I would say a very common strategy nowadays, at least as a baseline. So I think it's a nice choice if we want to learn more about this topic. All right. So the idea of this hands-on session was to make it as simple as possible to get into the flow of continual learning, but also for everyone to be used in a simple laptop or smartphone or whatever, because it's completely made for the Google Collaboratory. So you just need a Google account, and you can essentially run this notebook, change it, and do whatever you want with it. And it's part now of the Continual AI repository, where we run this project of multiple notebooks to get a feeling what it is to develop a continual learning algorithm. And yeah, so I'm gonna do it on this laptop, but you can also use your own and be async with respect to me. So you can just go to the Google Collaboratory. Then you can directly import all the notebooks from GitHub account. In this case, it's Continual AI. And
here you can search for Colab, which is our repository where we store all the notebooks, and this one is going to be Intro to Continual Learning. And here we are. So, alright, so here you can find all the information that you need if you are at home, you want to play against this notebook, or you want to do it not on Google Collaborative but on your own laptop. So a few more tips here. Well, and then we start with an introduction to Google Collaboratory. I'm not really a fan of Google Collaboratory because it took over the original project from, I don't know if you used it from Jupyter Collaboratory. So, and the open source as a version of this has been deprecated and closed by Jupyter, and someone was not happy about it. But yeah, this is the best you can find for having free resources, also a GPU K40. So if you want to play with a 12 RAM machine, virtual machine, this is the best you can have. And so yeah, the first part was to understand how it was to use Google Collaboratory. So for example, you can choose your runtime. In this case, it's a Python 3 interpreter for Python, and then you can use GPU, TPUs, or none. In this case, I have a GPU here selected. So disconnecting the virtual machine. So the nice thing is that you have an actual Ubuntu, I think, machine behind. So you can run commands, Linux commands, using the bank command before the actual command. So here we are just looking for the memory and the hard disk and if the driver, NVIDIA driver, is working. So this is the output. You can see that you have a pretty huge machine with 300 gigabytes available, and then we have a 12 gigabytes, sorry, of RAM, and then sorry, this is the 80. Okay, so everything is fine, and we can go on with our hands-on session. So unfortunately, they don't have a virtual machine already preloaded with all the toolkits for deep learning. Just the TensorFlow is loaded, of course, and sure. And so we are going to install here PyTorch 0.4. There is a new version of PyTorch, but I think that they didn't change the API from the 0.4 to the 1 and so on. So we're going to be fine, I think, to port this code to the new version. So it's going to take a few seconds. How many of you have tried Google Collaboratory before? Just a few of you.
I tried, especially for TPU,
Yeah.
to see how fast it is.
Yeah.
It goes very fast.
okay, so I think we have it installed. We can try it by importing it.
Example, okay, it is CUDA is available, so we can use it,
And then we can import a few things we're going to be using, George Vision, NumPy, Matplotlib for plotting something. Okay. So before moving on, I would like to know how many of you have already trained a neural network on a NIST? Sorry. It's like half of you. What?
Have a word for neural network.
Yeah, I mean, yes, no, but yeah, it's kind of difficult to work on Google Collaborative on more complex benchmarks. I tried, but yeah, the 12 gigabytes of RAM are sometimes not enough to do complex stuff. Okay, so okay, I think we can move on a, let's say, medium speed. So what we do here is to clone the collab repository from Continual AI, which has a few utils we can use. Nothing major, just to import the MNIST datasets as a NumPy tensor, a few NumPy tensors. But sometimes it's tricky because all these frameworks have different ways of loading things. Okay, so. I don't remember this error. I think there is another package called Collab in here. So. Sorry for this. Because the notebook, this is why Google Collaborative is not something to trust too much, because they changed the packages inside the virtual machine, so now the collab is conflicting with another package of, I don't know which enterprise, but anyway, it was a conflict with the name, so now I think we are set to go. Okay, so now we have in these four NumPy tensors the dataset, the MNIST dataset. So the X-train tensor now has 60,000 images, 28 by 28, channel because it's grayscale, missed digits dataset, and then we have the T-train, which are the labels, and the dimension of 6,000 int values, and the same can be said for the test set of 10,000 different images. All right, so now we can take a look at the images. Alright, so you can see here we have 0, 4, 1, and 9. These are handwritten digits for those of you that have not seen the MNIST datasets before. And we're going to try to classify them in 10 different classes. Okay. Okay, so still for the 0.4 API version of PyTorch, we need to specify the device on which to run our tensors and computations. That is kind of different with respect to other learning frameworks in which this is pretty much transparent. But yeah, so we're gonna define this use CUDA to true, and then a few more things that this device has depending on our own way to choose CUDA or to run this on CPU. The difference is not really much because this will be a very small convolutional neural networks we're going to define now, and so you can run it also on your laptop if you don't have a GPU, and it's going to be fine. Okay, so now we can define our neural networks. In this case, it's a very simple convolutional neural networks with two convolutional layers and a dropout layer and two fully connected layers. And so we can define them in PyTorch just by using the NN neural networks module, and then after we have defined these essentially weights or parameters of the network, we can define the forward function, which is going to be executed every time we pass to the network a new input, in this case x, an image. And the next thing about PyTorch is that you can change somehow the forward function depending also on the input data. So this is why it's more dynamic. And well, yeah. So in this case, it's pretty simple. We just have the image to be processed by the convolutional layer. Then we have a max pool operation, and then activation function ReLU, and then we do this again for the second level of convolution, and then we pass it to the dropout layer. Then again a max pooling operation ReLU, and then we have the fully connected part with this first fully connected layer, and then another dropout layer, and then a fully connected layer again, and that's it. So this was to define our model. Then what we need to define more is a couple more functions, so the train function and the test function, and then we are going to use all this stuff that we have written to run our continual learning, let's say, training procedure with different strategies. So the train part is pretty straightforward, I would say. There are thousands of ways you can do this, but this is one of those. And the idea is that you take the model, the device, the training data with the labels, the optimizer, the number of epochs, and then you do a nice loop over the entire training set, I would say. And you convert on the fly the data from NumPy to, of course, Torch tensors, and then you move them to the device. Alright, so then you put the gradient to 0 to start accumulating it, and then what you do for every step is to compute the output and then the loss through the functions offered already by PyTorch, in this case inside the functional module. So f dot cross entropy is going to compute the loss, cross entropy loss function, given the output and the actual labels y. Right, so then after we have computed the loss, manually here, loss dot backward, then we can have an optimization step that we have defined before. Sorry, I didn't mention it. Where is it? Ah, no, because we pass it to the function, okay, sorry. And then the same we do for the test essentially. So we have the model, device, and the actual images and labels for the test set. And in this case, we convert the model to be used only in an evaluation, so we don't store something. And what we do is to loop over with mini batches of 256 in this case are coded, but you can change it. And what we do is to do again this conversion from PyTorch, then moving the data to the device, compute the output, and then again compute the loss. And what we do more here with respect to the training, instead of doing an optimizer step, what we do is to compute essentially the number of correct predictions that we have made over the test set. And then we compute this, the accuracy essentially, and we print it on the screen. Alright, so then we define the model as the net we have defined before, and we move it to the device, in this case the GPU, and then we define the optimizer as a simple stochastic gradient descent optimizer with learning rate at 0.01 and a momentum of 0.9. Alright, so now we can train the model. So we do it for two epochs, and the loss is decreasing. The model accuracy is already after one epoch to 9% accuracy, and it's moving to 94. Right. So this was the building block we needed for our continual learning implementation, right? So now we are able to train this simple model on a NIST, and now we can start talking about continual learning benchmark based on a NIST. So what you're going to do is, there are many ways. So in research literature, there are many different papers that have been using, of course, a NIST to test new continual learning strategies. And so, for example, one of the possibilities to split the classes in different batches. So you, for example, encounter the first task in which you have to distinguish your digits 0 and 1. Then you move to the next batch, training batch, next task, and you have to distinguish the digit 2 from the third one, and so on and so forth. So this is a possibility, dividing tasks based on classes. 5 different tasks, two classes each. And then another possibility instead is to have a permutation, so that you have always the same task of distinguish the 10 digits, but you permute the input data so that the input distribution is always different among those tasks. And the complexity is pretty much the same among all of those if the permutation is random. So what we are going to define here is the I can add also that this idea of permuting and mixed data was proposed for the first time in a paper, Compete and Compute in 2012, and then has been used many times in continual learning as a reference point somehow. The first thing that a continual learning strategy has to tackle before moving on. And now it seems that it's going to be a bit, let's say, not considered much, since it seems to be just too simple to be accountable. So, okay, so let's define this procedure. I want to go into too much details here, but the idea is that you do just a random permutation of the pixels. So for each image is the same permutation, of course, And so even though for a human it becomes very difficult to distinguish the digits, for the machine is the same, exactly the same, because of course it has no concepts before digits. All right, so so okay, then we can use this function permit list to permit our xtrain and xtest, of course, the same way for each of these data splits. Okay, so this is the result. So this is the zero image, and this is again on the right is the same image after the permutation of the pixels, right? And yeah, so sometimes people they find it a bit amusing that how can a machine tell if on the right there is a zero or not? But if you think a bit more about it, the permutation is already the same, so the same pixel is going to be applied as well as in the first image, where we can distinguish many different zeros, even though some pixels are not light up the same way. All right. So right, if now we test the model that we have trained before on the original test images and then the test images after the permutations, right? So what we have computed here. So we have taken both the train and test after the permutation. And so we have just tested the method we have trained before on the first task, let's say the original task of distinguished digits from natural images. Now we have tested this model on the new task after the permutation, right? And as you can see, the model is not able to generalize to that task because it's very different from what has been trained on. Right? So we have 94%, the same accuracy we got before after training on the first task, but now we have 11% on the new task. So what we would like to do now is to learn also how to distinguish these digits, possibly not erasing the information of the previous task, right? This is the core idea of continual learning. So, so let's say now that we train our model, the same exact model, on the second task, xtrain 2, we train and the test again, test 2. So in this case, as you can see, we have managed to grow in terms of accuracy to the second task, but we have lost a bit of information of the accuracy of the previous task, right? Sorry, this was also on the first task. All right. Okay, do you have any questions?
Can you? Okay. Just to check what those 11% of the images was probably most similar to the original images. That's why.
The 11%?
When you tested the original trained module on the not permitted images.
Yes, yes. This was before. Then we trained.
Yeah, so it was able to recognize these 11% of images because they probably were very similar. So it was a matter of luck because I didn't check the permutation. It's static or it's random?
It's random. So, but in this case, we have 11, which is kind of random accuracy, right? 10% is random. So
yes, okay.
Maybe so it's a bit biased.
So there was some luck with random.
Yes.
Okay. And now it's 28.
It's now 28, yes.
Yes, so it's a bit higher than random.
Yes. No, but this is on the first task.
Yes, but
yes.
ruin the
Ruined the previous learning, but not completely,
Not
because
completely.
because of course something can be retained, especially if the model has been trained on the task, right?
Okay.
Like you train for the first class as 0 and 1, okay? Now, maybe in the future, if I try to fit this thing into alphabet as well, some people write I as like 1, seems like 1. So if this new task comes and the pre-learning is that, okay, this is 0 and this is 1, how do you analyze the new incoming, which is not related to the older one, but system will think, well, it's 1. Like, how do you plan to analyze this?
But now,
Classification.
no, I'm saying we are now working in a supervised context, right? So we know exactly what these data are and to which.
Analyze when the misclassification is done. Right.
Parallelize, you said
Penalize.
penalize, okay. Penalize, no, I get it now. Penalize?
Okay. So, if some other value comes up and it is given as like, it's like detected as 1, there is some penalized factor that you would write.
So you're talking about a conflict somehow, semantic conflict. But this is, let's say that it's true, it can be, there's a possibility that can happen, but this is, let's say, independent from the continual learning idea. I mean, when you have a classification task, you can always have classes that have somehow a conflict in the semantics. I mean, that for the lower level, maybe some features are shared, but then there's a conflict that you have to choose among those, right? In the end. So, yes, I think it's an important problem, but it's independent from the continual learning, let's say, idea.
Question. As an alternative to regularization, is it possible to implement some form of Bayesian updating?
Yes, I mean, AWC is somehow inspired to that, I would say. But the idea is that many continual learning strategies are somehow similar or used or been used in the past as a regularizer when learning from stochastic gradient descent. Because in the end, the stochastic gradient descent is kind of the same thing. You have many mini patches that you encounter over time, and you have to learn from them without erasing past information. In that case, you see again, because you do many epochs, you see again many data that you have seen before, but essentially you are trying to learn online, and you end up with the same problems if you don't use, for example, AdaGrad or other strategy for let's say, pool optimizer that you can use for learning more online than in a batch fashion.
Okay, and the second is quicker about the fact that you don't care about the fermentation as long as it's constant. It's like a differential entropy that is constant, so it's like the driving the constant to the next zero. I'm not expert about this fact. I mean, why does the constant fermentation doesn't it confound the learning process? I mean, it recognizes the features even if it's the same digit as long as the fermentation is the same among all digits. Does it have anything to do with entropy of information? I mean, since it has a constant fermentation should add something like a constant amount of entropy to all the images. So does it have to do with the gradient descent? And I mean, what is the reason for the fact that there is no confounding as long as the fermentation is constant?
Well, I'm not that much into the theoretical foundation or why it is the same, but essentially we are permuting pixels, and if you can train, for example, the same network and then you receive actually the same accuracy if you have a straight line of pixels, right? Because in this particular task, we don't care about translation invariance and so on and so forth, because they are always in the center.
Maybe it's because we multiply by constant matrix all the vectors of pixels, so it's always the
course. That's you just yes, it's just changing the position. Since we don't care about really much about the positions of the pixels. I mean, within a specific task, we care about the position of the pixel, but not to maintain them, all of them. It's the same as long as you do it for all the images, all the classes, or whatever. And you keep that. Someone else? Sorry.
I think I missed a point. Are we retraining the same model afterwards, or are we training from scratch?
Okay, so now what we were doing is just to show the phenomenon of forgetting, right? So the idea that you train on the first task and you're able to solve it, then you move to the second one, you train on this data, and you are able now to solve the second task, but you're not able anymore to solve the first one, right? So that's where we are now, and you have seen, and now we want to implement something to take this phenomenon and to fix that, so that we learn about the new task and we maintain also the knowledge of the previous task, having a single model. Right. So we're gonna see three different strategies. So the first one is the naive one. So what we have seen now. So just continuing back propagation on the new task is already there. So then we are gonna implement the rehearsal one. So just keeping all the data from the previous task and then shuffling them together with the new data task, and then train the model again, possibly updating the model with all this data. And then the third one will be the elastic way consolidation strategy I've talked about before, but we're going to go a bit deeper since it has a bit more of a theoretical foundation. So what we are going to do is to define, let's say, this continual learning benchmark by computing the second task here again and third task, and then putting them in a list of tensors, of lists for task 1, task 2, and task 3. So each of these lists contains the train tensors and the test tensors for each of the three tasks, right? Now here the labels are all the same because we don't need to change it. We have just shuffled the images. We don't need to change also the labels. This is why you see here the t-test is not changing among the tasks. All right, so. Okay, for the naive strategy, we already seen this, but we're gonna do that for the three tasks. Oh, sorry. I forgot to run this. Okay, so let's look at this code before running it. So what we do is to go through each task in a sequence, and we print the task ID here. Then we take the training data, so X train and T train, from the task, from the current task, and then we use the train function defined before. So we just add the model and we train this model on this data. And then what we do here, instead of testing just on the current task, we test on all the previous tasks. Right? No, in all the tasks, not just the previous ones. Okay, and so then we print the accuracy. All right. So let's look at the results. Okay, so when we train on task 0, and we test at the end of epoch 1 on the task 0, the accuracy is 91, right? So we have just trained on the first task and we get 91 accuracy. So then if we test this model on task 1 and 2, we get this accuracy. So even lower the random guessing for the second task and 12% for the third task. Then if we move to the second task and we learn about it, we can see here that it's growing to 64%, and but then we lose a part of the information we have acquired about the first task. That is 8% here. And then for the third task, of course, so we have not seen it yet, and it is still 12%. Then if we move to the third task, what happens is that we are now able to solve this third task, but then we further decrease the performances on the first task, and we are able to solve the second task to 36%. So this is a small recap on on these continual learning benchmarks. We have the same performance we have seen more or less on what we have done before with just 2 tasks. And this is the, let's say, average accuracy on all the tasks. So 36, 31, 40, more or less it is all that. All right, so then let's move to the rehearsal strategy. And in this case, what we do is to define a simple function to shuffle data, because up to now we have not shuffled data, which is an important thing to do pretty much always when training a model. But now we actually need it because we want to mold together the examples from the previous tasks and the current one. And so this simple function is gonna move around in unison. Why? Because data, because we want to move both in this case the images and the labels together, right? So we're not gonna do we're gonna go into this, but it's pretty simple. So now we reset the model and the optimizer, and then what we do for this rehearsal strategy is to do the same thing that we have done before, so going through all the tasks, but then what we do is to also do this step. So for each previous task, what we do is to take the past let's say training images and labels and concatenate them to the current training images, and then what we do is to shuffle them all together. So then we have X-train and T-train that have all the images and labels of all the previous tasks and the current one all shuffled together. And then what we do is the same as before, so we train our model and then we test on all the tasks. And as you can see, it's a bit slower than before because this is not a very efficient strategy. And you have to train all again and again on the same data and further increasing your memory every time you encounter a new task. And in this case, you can see that we have pretty much the same situation on the first task. But then you can see that we're able actually in this case to improve our performances on the previous task, and so on and so forth till the last one. So we have a very let's say improved accuracy on all the 3 tasks, so that are better to be trained together than in isolation, as we would expect. All right, so. What about elastic way consolidation then? Well, in this case, you can find all the details, of course, in the original papers, or the original paper of this that is linked in the notebook. But essentially, is based on on the idea of adding a regularization term to the main loss to change as little as possible the weights that are important to the previous distribution, to the previous tasks. So how it is done? So let's say that we are moving from the first task that we're going to call V to the new task we are going to call new. So the loss of the new task, when we define it, is going to be like that. So L of new sign is equals to the L of new loss, the cross-entropy loss function for the current task, so the task new, that you can define as you want, plus a regularization term. So plus lambda, which is just an hyperparameter term, and then we have the sum all over the possible weights, k, of these products. So we have the delta, which is going to be the importance of that particular weight, times the difference of the current weight, theta k, with respect to the optimal weight before starting training on the new task. So we are actually saying, intuitively, how far we are going to the previous solution with that difference, and then we are weighting this by the importance of that particular weight, so that if it is important, the weight is important, and the difference is high, we have a very high regularization term there, which is going to increase the loss and then be, let's say, penalized in this change. So in this way, very naturally, we are able to minimize the changes in the weights that are important. Now the question is, how can we define the importance of each weight? And in AWC, there are many ways of doing it, but in AWC, the weight importance is based on the concept of official information. This is a statistic concept, and is based on the idea of how much information is carrying out the each weight, theta k, with respect to the random variable x in the log likelihood function. So that's the definition of the Fisher information, and can be approximated as the variance of the gradient of the loss function. So it's very simple in the end to implement, but it has this, let's say, theoretical foundation. Oops. All right, so in this case, we're gonna define two dictionaries. So the Fisher, that is the let's say the weight importance we're gonna keep for each weight, and then we're gonna also keep. This is a bit heavy, I would say, memory in the sense that you have to keep two essentially snapshots of the same network because you have the importance value and the optimal values, the first term on the difference we have seen before. And then we have also the hyperparameter lambda here that we defined at 0.4. And we reset again the model and the optimizer. And then what we do here is to define a particular function on task update. So given a task and xmap, tmap, what we do is to compute essentially the Fisher information in this step. So what we do is to accumulate the gradient for all these memory, or say all the training examples. We can do that. So we are going through all these examples in mini batches as before. All right. Yes. So here we just accumulate all the gradients. Then we for this task we create a dictionary inside a dictionary, and then this is just the magic, let's say, of computing the importance of the weight, because what we do is just to clone the optimal parameter here. Not really important, but here is the computation of the Fisher information, just the power of 2 of the gradient, because if we do a bit of math, there is essentially the variance of the gradient, and that is, it can be shown to be just that simple, because the average is zero in particular points. This is the small function we're going to use now within the train AWC function, which is going to look the same again with respect to the other strategies. So going through all the tasks. Sorry, this is not the last one. Sorry, train AWC function instead of just train, because we need to actually add the regularization term to the loss that it was not included in the train function we had defined before. So what we do is doing exactly the same as before, but here we have the regularization loss, as you can see. So the loss is computed here from the cross entropy, L of nu, and then we have the regularization loss here. So as we have seen, the fish for each weight, the Fisher times the difference from the optimal parameter minus the actual parameter, and then we square it by 2, and then the sum times the AWC lambda will do the actual regularization term. Okay, so having defined this, we can run again our experiments. So again, here we have, after the first task, we have 95% accuracy on the first one, and very low performance on the second one. And then again here, we can more or less keep the information on the first task, and we lose a bit on the second one here, but let's say the average accuracy is a bit higher. And here we can plot these results. Let's see if we plot them. You can see that the naive strategy is the worst one, of course. Then we have the WC strategy is going at least growing, and then we have our, let's say, upper bound. In this case, the rehearsal approach, which is very high and can keep pretty much all the information of all the tasks. But there are a lot of strategies that have been developed in the recent few years, I would say. They can, of course, beat AWC and I don't want to say reach rehearsal strategy, but let's say going pretty near in some cases. All right, so this was the hands-on session. Do you have any questions about this? Meta questions?
Around for more epochs AWC would reach precision, I suppose.
It depends, I would say, on a lot of things, the hyperparameterization, the type of the optimizer.
But it's trained in a step, so you don't mix with the as the previous one. Like
no, you mean like adding more iterations,
yes.
Each different tasks. In general, if you push too much, you risk to forget more. More to the past, because you are just optimizing more on the weights on your current task.
Yes,
but it depends a lot on the strategies, the other parameters. It's not a definitive answer.
Mm-hmm.
If we add more tasks, I guess that the EWC would saturate at some point. There are some studies that say more or less.
So we're pretty much really on this topic. So benchmarks nowadays, they deal with a number of dozens of 20 tasks or batches. It's difficult to say how we're gonna scale in a number of hundreds of tasks. But yeah, if you look at all the graphs of this strategy, they all tend to saturate, and it's gonna be a nice improvement when we actually can have lifelong learning systems that you can live with as they after deployment, let's say, and they will grow in terms of accuracy. And yeah, it's a bit early to say, let's say.
Couple of questions. So it wasn't clear to me how you select the regularization parameter that you love for. And the second one, if you have to start with continual learning in your system, which one do you suggest to start with?
So for the first question, for this notebook, I just choose the first, let's say, parameter that I could, like with a couple of experiments. But of course, if you want to do it properly, you need to do a bit of cross-validation or whatever, or a grid search of the hyperparameter as you would do for the other hyperparameters in deep learning. Then for the second question, I mean, these are pretty unstable if you want to use it in production on real systems. So I would suggest to use them. Some of them are interesting, a bit, let's say, stable, but maybe they provide you a very little improvement in terms of accuracy with respect to the naive strategy. So you in general, you don't want that. Then another point is that it depends a lot on the application. If you don't, let's say, you don't care about a very high addition in accuracy, but you care a lot about not decreasing it, for example, then you can use a lot of these strategies without any additional memory overhead or whatever. But if you care about a really increase in the performances during time, then I always suggest to real products, real applications to use a bit of rehearsal, because a very small percentage of rehearsal can help a lot. So you combine that with another continual learning strategy, and you have a lot of better and stable results.
Maybe I'm not getting a point of rehearsal, maybe, because very simply, probably you just created a data set that is double the size of the first one, right? So first, why don't start from scratch? Why is it better like this and not from the beginning? Also because at the end of the third training, you have seen the first data 3 times.
Yes.
So you may be biased toward the past data, right?
Well, for the rehearsal, this, so for my experience, the idea of the best accuracy you can have for this sequence of tasks is to train them all together from scratch. So what I call the cumulative strategy. So if every time you encounter a new piece of data, the best possible accuracy in general is to accumulate all the data and start everything from scratch.
It's also the constraint.
From random initialization of the network. So this is the best you can do, but it's very not efficient because let's think about instead of a list of ImageNet. If you add a new class, you have to start from scratch. It's crazy. So that's a point. Then for the rehearsal approach, using all the data in general is not really necessary. In this case, it's the full rehearsal part, and yeah, I don't think it's gonna be biased towards the first task, but anyway, it's an overshot, I would say. Most of the times you have to keep like 10% of the data of the previous tasks, and you are fine. You can pretty much maintain the level of accuracy of that you have had before on these tasks.
Also have another question, sorry. The point about the adaptive optimizers. When you start a new task, if you reset it, you can get a step so high that you just forget whatever.
Yeah.
Right? So it's just starting from scratch. If you do such a big step that everything is just, I mean, could it be?
Yeah, it's part of the problem. I mean, the optimizers are part of the continual learning, let's say, solution or problem. In general, some people, they reset the optimizers, but they keep the weights. So that they start slow when they learn a new task, so they can control it very properly. But the weights are from the previous task, right? And the parameter of the optimizer, like if you use a very complex optimizer, there can be parameters there, but they are generally reset to, like you said, start, let's say, from scratch with that respect.
Sort of using the previous weights as a sort of pre-training model.
Yes, yeah, the weights, of course, because it takes a lot to learn everything. But the weights of the optimizer, like if you're using AdaGrad or whatever, can be some hyperparameters there. In that case, people tend to reset them, but it's empirically validated, I would say.
Thanks.
You know, while I was listening to your presentation, I had a totally new idea. Basically, just think about this. Say you have 20 tasks, right? In the beginning, you just train 20 networks with one task per network, so you have optimal accuracy, right? Afterwards, you train an additional network, which job is just to classify one entry based on the task. So to tell the task it belongs to. So if you have 20 tasks, you know where a piece of that, what task a piece of that belongs to. So afterwards, you can further optimize this step because perhaps two tasks are similar, so the classifier is having a bit of a hard time. So you can decide to collapse these two networks to one, so you won't end with 20 tasks, but perhaps a lesser amount. In which case, by collapsing, I mean, you can just use one of the techniques you explained here. You should have a pretty high accuracy on both tasks, right? In the beginning, you end up with a slightly more complex network topology, which classify two sub-networks. And if you think about it, you just have perhaps a couple of layers. It shouldn't be hard to classify one data, but determining the task. Therefore, the inference time should be slightly higher, but pretty much cheap. Of course, the networks will have a higher size, but the training time should be pretty much the same, if not better, and so inference. And you would have probably the best accuracy you could ask for.
Well, I don't know. I would like to see like a couple experiments and
Why don't you perform
more in depth.
Why don't you make those experiments?
No, the idea is the vision for continual learning is to have a single model, because you can have all these tasks solved very efficiently with a single model, and that's it. So the idea of continual learning is to avoid having multiple models with a complex model, because you can actually have a single model that can solve all of them. And the idea is to squeeze this information continually inside a single model. And of course, there are many, especially for practical application, there are many solutions. But the idea, at least, of the paper that.
Well, but excuse me, this is a concern. You could just upscale the network, add layers, and therefore you would have enough room, and you just keep training, and you would have enough room to completely discern every task. But these require higher inference time as well as.
There are some strategies that deploy a growing network approach or whatever. But yeah,
unified, in my opinion, less efficient than that I described. But if there is concern, you can just achieve that. Increase everything.
I don't know. Right. Maybe you're right. So I'm waiting for your next paper about it. So someone else? How far are we? Time?
Just right with ImageNet.
No, so I think that there is just one particular approach that has been tried on ImageNet. Because you know, when you do continual learning, you add essentially another level of complexity, which is time, and you have many different tasks, many different batches that you have to learn sequentially. You cannot parallelize, you cannot do anything, because the task is to learn sequentially. Yes. So there is this big problem, and then you want to be like invariant with respect to the order of the tasks of the batches. So you have to run multiple runs, multiple strategies, multiple benchmarks, and if you have all this level of complexity, you end up with a week of waiting time to see the results of your new algorithm. So the idea for now is to test on medium level benchmarks, and this is why we propose a benchmark which is called Core 50, and to get an idea of the level of complexity of this. This is a video benchmark, but it's still 160,000, images, 128 for 128. So this is, let's say that this is the complexity that takes, like, for one subject, it's like 30 minutes to go through the entire benchmark, because we have like, 10 batches of 10 classes each. So this is the complexity that takes like 30, 40, 1 hour. There are some strategies that takes 1 hour and 30 to run. So if you just won't compare to the other guys we are doing, then this is already a big, let's say, overhead.
But yeah, the future will be on tackling problems that we already tackled in terms of deep learning and the vision community. Someone else? Right, so thank you very much for your attention.